All right, so we left off talking about stereochemistry and reactions. Oh, that didn't cut right. And we left off talking about doing reactions on molecules that have what we call pre-existing chiral centers. In other words, you start out with a chiral molecule and then you react it with something that's achiral to get a unequal mixture of stereoisomers. All right, so we're gonna finish out this concept and then we'll start something else. So let me paste this down here. All right, so the question now, we're gonna look at the same molecule. But the substituent on the chiral center is bigger, right? So that substituent actually looks like this now. Oh, yes, it's got 3 tert-butyl groups on it. I'll just abbreviate the rest of the chain. So let's look at the question. The question asks now, when the reaction at number 2 is carried out with this molecule with the tert-butyl substituents on it, would you expect the ratio of stereoisomers to change? Would you expect the major product to be increased? What do you think? Make that substituent that's at the chiral center bigger. What should happen to the ratio of stereoisomers? We're looking at this reaction right here, the second one. So we have our we know what our 2 products are. But the question is now, if we make the substituent at the chiral center bigger, how does that change the overall stereochemistry of the reaction? So the group that I have circled there, I'm not sure what color you can see. It looks like an orange highlighter to me. If that group is bigger, will it change this ratio that we said was something like 54 to 46?
So you said essentially if we make the chiral center group larger, if it would change it?
Yes.
Well, yes.
Okay, good. I agree. It will change it. Will it force more? Okay, so what would the ratio? Just give me an estimate. What do you think? I mean, we don't know because we have to actually do a reaction. But when we say 54 to 46, one of those is favored. So we're going to say that this is favored. And this is 46%. So which number is going to go up in this case if we make that group bigger? And I'll cut this out and put it on the same page. So we'll have a point of reference. All right. So now this is we're going to do the same reaction, but we're going to make that group bigger. Go ahead. You can finish your point. I apologize for that. I just wanted to make sure we were clear on what we were looking at.
I can see it. If you make it larger, I assume that the steric hindrance would increase. Probably for the whichever group has them on the same side would probably has them both going in one direction towards or backwards. That would be the group that probably would. That's the part I'm not even sure, but I'm gonna just go ahead and give my best guess is that
go ahead.
that group is going to be decreased.
Yes. So you're saying the 46% is, we know that the reason it's 46% is because of the orientation of those two groups. They're on the same side, and normally that's a bad thing, right? So if I made the group bigger, that's going to disfavor that isomer even more. So you're right. So in this case, if I make it bigger, the question it asks is, would you expect the major product to be increased? When we say major product, that's just the product that's present in the highest amount, like the highest percentage. So let me put that here. The highest percentage product. So this is 54%, and the other one's 46%. So 54 is my major product. All right, but if we did it on this, let's just draw the two products that we get from that. So we get this product. That's one of them. And the other one, I'm just going to copy it. Right, the other one is going to be here, right? But this is going to be different. Is that right? So the question is, which one of these is going to be major? Which one is going to be minor? We know based on the previous reaction that this is the favorite isomer. Right, favorite because the two groups are on opposite sides. Right here and here. Over here on the same side, so this is going to be the isomer that is disfavored. Right. So the question is, would you expect that to be more of the favorite product for this reaction when you change that substituent? And I think that you, Cecilia? I think your answer to that was yes. Is that right?
Yes, sir. That would be increased and the other one be decreased.
Yes. So yes. And that's going to be due to sterics. All right. So yes. All right. So hopefully you're getting a grasp of when you do these reactions with pre-existing chiral centers that you are able to manipulate the product distribution based on either the size of the group or how close it is to that reactive site. So let's go up here. Any questions before we move on? All right, so let's go up here. We can answer these last few questions on here, then we'll start talking about this other section. So this is a different reaction. Anybody remember this reaction from part one? If you got an A,
Didn't you say?
Go ahead.
Oh, never mind. I was gonna say No, I don't remember actually. No.
You got a double bond in the presence of hydrogen peroxide and sodium hydroxide. I need some flashcards. This is an epoxidation. It's an epoxidation. Anybody remember what that does to a double bond? What is an epoxide? What does that functional group look like?
Doesn't it turn the alkene into an alcohol group?
No, actually it turns it into an ether. It's a cyclic ether. So if I take an alkene and I react it with hydrogen peroxide and sodium hydroxide, I get an epoxide. All right. So that's the reaction. It's an epoxidation. Right, epoxide is a cyclic ether. So if I have this alkene and I got that pre-existing stereo center right next to it, and I'm reacting it with hydrogen peroxide, what is that epoxide going to look like? Because the oxygen at carbon 2 is definitely going to be chiral. So what would it look like? What do you think? I have a tert butyl group here. Wouldn't I get this as one of my products? And this as the other one. I should get a mixture of stereoisomers because my starting material is chiral and my other reagent is not chiral, the hydrogen peroxide. So I should get a mixture of stereoisomers that look like that. So now let's see if we can answer these questions. I'm gonna have to send y'all something like a refresher on these reactions because this is critical. If the reaction stumps you, then getting to the part for part 2 that we need to talk about is irrelevant. So definitely, I have a couple of things I can send. I'll send them out when I send this stuff out for today. All right. So what do you think for question 8? Which product do you think is favored? We already have it drawn, so we just need to pick which one is favored, or the one that we think is favored, based on what we know about reactions that happen at all molecules that have pre-existing chiral centers. What do you think?
The product on the left.
This one?
Yes.
Okay. And this one will be disfavored. When we say favored and disfavored, I need you to understand that what we're talking about in this particular case is which one is the result of a lower energy pathway to product, right? I showed you that at the very beginning, where you go through your transition state and then to your intermediate, and then well, this doesn't have an intermediate, but the reactions that we looked at initially had intermediates, but the goal is to follow the pathway that has the lowest activation energy. So the one that's with the two groups opposite to one another is going to be favored, right? And that's all due to sterics. All right, so that's a higher energy product with those two groups on the same side like that. All right, let's see if we can answer these questions. I'm not going to intervene. I need somebody to read it and answer it. B for B and for C, because we already have done A. And if there's something that's over your head, say something. Don't just write the answer down and turn it in without understanding what you're doing. So if anything goes over your head, ask a question. Go ahead.
Okay. What do you think what if I change the terbutyl group to a methyl group?
Mm-hmm.
So I think the answer is the ratio of stereoisomers will, I want to say will not change.
Okay, let's think about it now. If I took the same molecule, but instead of a terbutyl, I just put a CH3 here. What have I done? I've made the substituent on the chiral center smaller, haven't I?
Oh, so it's it would be closer, and the ratio of stereoisomers would go down.
It should decrease, right? If I make this group smaller, if this group right here is smaller, that means that there's less steric hindrance at that site. That means that the reaction is not going to require as much energy. And so the ratio is going to, the disfavored product is going to be more accessible. So that's going to make the ratio go closer to the two stereoisomers being equal. They might not necessarily be completely equal, but if I make this smaller, right? If I make that group smaller, then it's going to have less influence over the outcome. So that means that that both reaction pathways are going to be not equally accessible, but the other pathway is going to be more accessible. So that means that the ratio is going to go down. That means more of your minor product is going to be formed. All right, so more, remember, this is all based on two ideas of either size or proximity. So the size of the group matters, and then where it's located matters. Right, so let's look at the next question. What do you think will happen if we move the terbutyl down to carbon 6? So you see right now it's on carbon 3, and it's right next door to the reactive site. What happens if I move it here?
So I think the ratio of stereoisomers will go up. Well, actually, I think it would be equal.
Good choice. Right, it literally, because look where the stereo center is relative to the reactive site, right? So it really is not going to exert much influence over that reactive site at all. So you end up getting, what do we call it when the ratio of stereos isomers are equal, or is equal, not are?
A racemic mixture.
End up with a racemic mixture. we're probably gonna get a racemic mixture. All right, it's just too far away to have any influence. All right. So when we think about chirality, we talked about configuration, we talked about RS, we talked about handedness. We've talked about how to locate and identify chiral centers, how to prioritize, all of that. And then we've also talked about how chirality can influence reactions, right? You have a chiral center present, and it's going to influence the outcome of the reaction, and you're going to get an unequal mixture of stereoisomers. So now, the next section that we're going to discuss is going to be dealing with alkyl halide synthesis. So it's going to take us right into that. It's totally different. It doesn't have anything to do with chirality. It's just the next topic if you look at the syllabus. Right, so right, so when we talk about alkyl halides, we're going to talk about how to make them, and how to apply them. So for the synthesis part, we're going to talk about two methods, but one of the methods is going to have like 3 different reactions that you can use. All right, so one of them is allylic bromination, which we're going to start with today. Actually, I want to start with the alcohols. And the other method is conversion of alcohols to alkyl halides. And I'll talk about what a alkyl halide is and all that stuff in a second. Right, and then for the application, we're going to talk about
There's no paper anywhere. You couldn't have put that stuff in my bag. Because
for the application, we're going to talk about organometallics, and I'll talk about that too, and how to make them, and some of the reactions. All right, so I actually want to start with the conversion of alcohols to alkyl halides. We're going to start there instead of allylic bromination, because I don't want to get bogged down in a discussion about resonance, because I know that's coming. But we'll get to allylic bromination. So let me talk about that. So first of all, what is an alkyl halide? All right, you should remember this from organic 1. It's a very simple functional group. You have an alkyl chain, and on that chain, you have a halogen. Right, you know halogens from the periodic table are group 7 elements: chlorine, bromine, fluorine, iodine, astatine, so on and so forth. And then you have, so that's the halogen, and this is the alkyl part. So when you have a halogen on an alkyl chain, we call it an alkyl halide. Right? The reason why we're going to talk about alkyl halides is because they're very versatile reactive intermediates. Right? You can use them to synthesize other molecules pretty rapidly. They are good for coupling reactions, which we're going to talk about. And in those coupling reactions, you make new carbon-carbon bonds. And they're good, also good for substitution reactions. So you can use them to add new functional groups. All right, so they're really versatile. And one of the methods to make alkyl halides is to take an alcohol. Let me add another page. All right, one of the simplest methods for synthesizing alkyl halides is to take an alcohol and then react it with some halogen source. So I'm going to say Z, X. And then in the product, we have X plus O, Z. All right, so one of the simplest ways to make alkyl halides is to take alcohols and convert them into alkyl halides. So this is my alcohol. Everybody should be familiar with that functional group. And this is my alkyl halide, right? And again, a lot of what we talk about is going to require a working knowledge of part one. Let me say this up front, because I've taught this class forever. The biggest impediment to like doing well in this class is there are two things. First is functional group recognition, knowing the difference in the alcohol, a halogen, a ketone, aldehyde, ester, knowing your functional groups. So if you struggled with functional groups, you need to refresh yourself on that. The second is recognizing like the reactions that we've done in part one, right? If those reactions are fleeting and they escape you, then you need to refresh yourself on those because a lot of those reactions you're going to see again. And then if I had to say add 2A is resonance and arrow pushing. Like that really, if you had a problem with that in part one and didn't address it, then it's going to continue to plague you in part two. So my suggestion is to, again, refresh yourself on your functional groups, refresh yourself on the resonance, arrow pushing, and on the different reactions from part one. All right. So this reaction falls under the class of a specific type of reaction. In part one, we taught that there are 4 different types or 4 different classes of reactions. Anybody remember? Or remember at least one of them? So it's substitution, elimination, rearrangement, and addition. So substitution, elimination, rearrangement, and addition, right? This type of reaction right here, where you take an alcohol and turn it into an alkyl halide, it's a type of substitution. Right? Anybody remember from part one, the two types of substitution that you studied? There are many, many substitution pathways, but you only studied two in part one, or at least were introduced to two of them. Anybody remember them? One of them was should have been SN1 and the other SN2. Does that sound familiar to anybody?
Yeah.
Okay.
Yes, it does.
All right. So these alcohol substitutions or these alcohol conversions are either going to fall into the category of a SN1 or SN2 type substitution. They're going to be one or the other, depending on the alcohol substrate, right? If it's a tertiary alcohol, and I'm abbreviating alcohol as ROH, it's going to be SN1. If it's primary, it's going to be SN2. And then in between, depending on the conditions, will be a secondary. Secondary can be either SN1 or SN2. It just depends on the conditions. All right. And while I'm saying that, let me give you what I mean when I say a primary alcohol. So this is OH. Right, this is a primary alcohol. It only has one bond to carbon. This is secondary. Right, you can see that it has two bonds to carbon. Well, it has, let me not say that. That carbon where the alcohol is bonded to two carbons. Right, the carbon here where the alcohol is bonded to one carbon for primary. And then for tertiary, you can see this is and that position, the carbon where the alcohol is, we call that a carbonyl. So that carbonyl carbon has now 3 carbons attached to it. So it's tertiary. All right, so primary, secondary, tertiary, you're gonna hear that terminology a lot. So that's why I'm introducing it now. So primary alcohols, typically when they undergo substitution, is SN2. Secondary could be either or. Tertiary is SN1. All right, any questions so far? Another thing you're going to notice is that in the mechanism, I'm just going to give you a generic mechanism to begin with. In a mechanism, is generally stepwise, right? It's generally stepwise. So you have multiple steps to get from point A to point B, and you have different intermediates in between, right? If you remember from part one, a stepwise mechanism has intermediates, right? What's the other type of mechanism from part one? We talked about two types, talked about stepwise mechanisms, and then we also talked about another type of mechanism. Anybody remember? The other type of mechanism is concerted, right? There's no intermediates. You go straight from reactants to products. right? Anybody remember what that looks like in terms of energy diagram? What a concerted mechanism looks like? So if you have an energy diagram here, where this is time and this is energy, right? This is reactants, products, transition state. That's concerted. For stepwise, it's the same. Reactants, transition state, intermediate, another transition state, and then depending on how many steps it is. Right, so and this is the same time and energy. Right, so for most of these alcohol conversions, is the overall mechanism is going to be stepwise. So it's going to involve some intermediates. So a generic mechanism is going to look like, let me just take the same alcohol from up top. And you'll see this in the video to reinforce it when I send that out. So you have some halogen source, right? And then your alcohol is going to act as a nucleophile and react with that. Right? So whatever the counter ion is, or the substrate is, where the halogen is, it's going to end up here. Right, so in a generic sense, you have your halogen source, it reacts with the alcohol. And now this is the key. This is always, every one of these reactions is going to have a step like this first step to make the alcohol a better leaving group. Let me put the hydrogen back on here. All right, so now my alcohol is a better leaving group. And depending on, again, the method, if it's SN2 or SN1, I'm just going to show it as SN2. Now the halogen can come in and substitute for that. All right, so you end up with the alkyl halide, and then whatever the alcohol ends up on it too. So it just depends on the method. If it's an SN1, that leaving group is going to leave first. If it's SN2, it's simultaneous. So the nucleophile is coming in the same time the leaving group is leaving. But we'll talk about that more as we discuss this. Any questions so far? All right, I know this is it kind of seems like it's in the weeds, but it's really not, because the arrow pushing and the mechanisms and formal charges and all that stuff. I mean, you're expected to have a little bit of that with you. So, but are there any questions? Any questions about the arrows, about anything while we're here?
No, sir.
Rearrange these pages right quick. let me just need to put the alcohol stuff up further and move the allylic bromination stuff to the back. Because I think the alcohol synthesis is a little bit, it's going to be easier to track it than the allylic bromination, because I already know that resonance is going to be a sticking point. So I'm going to send you some resources so you can refresh yourself on resonance. If you had a problem with it. If you didn't, then you're good. All right, so let me, without getting stuck, let me introduce you to the methods, and then we're going to go through each method, mechanism, all that. Right, so for primary and secondary alcohols, you got two methods that you can use. One of them is to use thionyl chloride, which is SO, and I'm going to explain all this stuff when we get to it. And pyridine. Right, and then the other is to use PBR3. Right, those two methods, and I will explain it, go through the mechanism, arrows, all of that. Those two methods are used to convert primary and secondary alcohols. Right, and then if you have a tertiary alcohol, we're only going to discuss one method, and that is just using HX. Right, where X is chlorine, it can be bromine, it can be iodine, it can't be fluorine. But any of these three halogens you can use to convert a tertiary alcohol into an alkyl halide. Right. One of the things about organic synthesis is knowing which tools to use at which time. Right. It's just like anything else. If you were building a house, you wouldn't use a hammer to drive in a screw. Right. You wouldn't use a screwdriver to drive in a nail. So knowing which reactions to use at which times and on which types of substrates actually matters. Those who do that very well are really good at, and I'm not talking about class-wise, I'm talking about just period. Because we started out with that Paxlovid molecule. That thing probably, I want to actually look and see if I can find a synthesis for that, but it probably involved several steps. And each one of those steps to make a fragment and then bring all the fragments together at the end. I'm certain that the groups, the research groups that synthesized that molecule, whoever did it, they went through countless numbers of publications and references to find methods that actually would work to make certain fragments. So knowing what to use and when to use it, it matters. So I like to think about doing organic, like the reactions are like tools in a toolbox. So you always have to think about what you need. If I want an alkyl halide, okay, I'm making alkyl halides. Then you start thinking about what ways do I have to make them? And then you think about what you have. What am I starting with? When you think about what you're starting with, then you'll know which method to use, because the substrate is generally going to dictate what method to use, because everything doesn't work on every substrate. So that's kind of the thinking. All right, so we're going to stop here. I actually stopped on time today. I'm going to post the notes. I'm going to send you some videos for alcohol to alkyl halide conversion. The quiz for that, I think, is already open. And I'm gonna send you some stuff as a refresher, a couple of videos for that. And I have a handout from Organic One that I'm gonna send you. It has up all the reactions on it, at least the ones that you'll need to survive part 2. It has all the reactions on there. So I'll send that to you shortly. Any questions about anything?
I have a question